So welcome all to week 2 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So the topics that we're going to cover today are based on week 2 content of the course. And broadly, I'm going to cover what are linear transformations. Then I'm going to go to norms and inner product spaces. Later, I'll also do some examples on finding out eigenvalue and eigenvector of a matrix or a transformation. Okay. So yeah, so last time we did what are vector spaces. Today we are going to define functions on vector spaces. Okay. So linear transformations are nothing, but they are functions from one vector space to another vector space. These are vector spaces. Okay. Satisfying these two properties. Okay. So linear word, if you see the word linear, linear means like if you have something x1 plus x2, something of this form. So what linear transformations mean, if you are finding the value of v1 plus v2, then it should be equal to t of v1 plus t of v2. So in fact, it means like, let's say if it is a single variable, so f of x should be something of form ax. Okay. You can't have square or square root or those kind of things. You just need to be linear. Okay. Second property is if you multiply your input with some alpha, then that alpha comes out of the function. Again, the function is of something of this form. So let's take a counter example. A counter example can be, let's say f of x is equal to x square. So this is not a linear transformation because it don't satisfy any of the two properties. Let's say if you calculate f of 2 plus 3, so this is 5 square, this is 25, and this is not equal to 2 square plus 3 square, right? Also, if you take, let's say 2 into 2, this is 4 square, 16, right? This is not equal to 2 multiplied by 2 square. Okay. So this x square is not a linear transformation. In this lecture or in linear algebra, the kind of functions that we are interested in are actually which satisfy these two properties. So we are not interested in functions of form x square or those kind of functions. We are interested in functions which satisfies these two properties. Okay, these are two very basic properties that v1 plus v2 you will split, and if you have alpha multiplied by v1, alpha will come out. Okay. I forgot to mention, if you have any doubt at any point in the content, you can stop me there. Either you can unmute yourself and speak, or you can type it in the chat box. I'm monitoring the chat box too. Okay. Okay, so this is what a linear transformation is. So now some fancy notation. So if we have a linear transformation from a vector space to itself, so you look at the definition carefully. Earlier we had a linear transformation from some vector space V to some vector space W. Now if you have a linear transformation from V to V itself, for example, if you have a transformation from R2 to R2 itself, then those kind of transformation are called linear operator. This is just the name. Okay. If you have a transformation from vector space to your field, okay, field over which your vector space is defined, that kind of transformation is called linear functional. Okay, these are just two names that you might come across at some point. Okay. Okay. So transformation, again, transformation is nothing but another name for function. You can just treat this as a function. Okay, so this is a linear function or a linear transformation. Okay. Okay, now we have a property of linear transformation that it will always map 0 to 0. Okay, now this is not something that is in definition, but we can derive it from the definition that is given to us. Okay, let's see how we can prove this thing. Okay, now you know that 0 can be written as 0 plus 0, right? Because we know that for any element a is a plus 0. So a can be 0 too. So 0 is equal to 0 plus 0. Okay. So if we have t of 0 plus 0, this is equal to t of 0, right? Then using the first property of linear transformation, it's split. So this should be equal to t of 0 plus t of 0, which is equal to 2 times t of 0. Okay. So what does this mean? Like if you take this thing from here and you take this thing from here, this would mean that t of 0 is 2 times t of 0. When is this possible? This is only possible when t of 0 is 0. Well, like if it takes any other value, then this thing is not possible. Right? Okay. So why I covered this property is when you have to prove or disprove, or you have to check whether some transformation is a linear transformation or not, this property helps you rule out many non-linear transformations. Okay. So you can simply check whether t of 0 is 0. If it is not, you can straight away say that it is not a linear transformation. Okay. Okay. So here are 5 examples that I have included. Okay. So you have to check for each of them whether it is a linear transformation or not. I'll write the properties here also, and I'll give you 5 minutes to solve these. And you can type it in the chat box. What do you think about each of them, whether they are linear transformation or not? Okay. So this should be equal to t of v1 plus t of v2, and t of alpha v1 should be equal to alpha times t of v. And a bonus property that I gave you is that t of 0 should always be 0. Okay. So it's 6:12 right now. Let's you try it for 5 minutes and type it in the chat box. What do you think the answer is? Let's hear about A first. What do you think? Whether A part is a linear transformation or not? You can type it in the chat box. What do you think? A is a linear transformation? Yeah, somebody said that. No. Others also, can you please try and tell whether A is a linear transformation or not? Oh, Priya, you have raised your hand. If you want to speak something, you can unmute or type it in the chat box.
Using mobile, no, I was finding it. I couldn't find chat box. That's why I was.
Okay.
First one is, according to me, it is non-linear.
Yeah. So I'll solve the first one and then again give you some time for others. So we'll just use the third property that we just proved. So if we put t of 0 comma 0, so a1 takes the value 0, a2 also takes value 0, then its answer would be 1 comma 0, right? This is how this function is defined. So this is not equal to 0. And we said that for any linear transformation, t of 0 should be equal to 0. Okay. So the first one is ruled out. I'll also solve one more question. So if you look at the E part, here also if you take t of 0 comma 0, this is 0 plus 1 comma 0. Again it's 1 comma 0. So using the same property, this can also be ruled out. Now you take some 1 or 2 more minutes to solve B, C and D part. So I'll give you a hint. None of them are linear transformation. All of them are non-linear transformations. But you need to find the reason why they are non-linear. Which property do they violate? That you have to find out.
Second one,
Second
due
one
to
was
square term.
there is a square term, so it would violate first property or second property. So if you look carefully, it would violate both, right? You can use any of the property to say that it is not a linear transformation. So if you have, let's say, P of alpha times V1, so it would become alpha A1, comma alpha A2. This would be alpha A1, this would remain as it is, but alpha square A2 square, right? So you can't take one alpha out. So if you take alpha out from here, still you will have one alpha left over here. So it is not equal to alpha times V1. So this is again not a linear transformation. Again, if you see anywhere square, sine, mod, you can rule out those kind of linear transformations simply. Okay, you can simply rule out those linear transformations. Okay, so there are few more examples. I'll include this sheet. If you want to practice, you can sort of practice. These examples I think I took from the book by Fred Berg. So I'll quickly go over why these are nonlinear transformations. Again, you see a mod over here. Because of the mod, you can ignore. Over here, you have a term x1 minus 3, right? So if you take transformation of 0, comma 0, you will get 0, comma minus 3, comma 0. So you have a minus 3 over here. So t of 0 is not equal to 0. That's why you have, that's why this is not a linear transformation. Okay. Any doubt till this point before we move ahead?
Clear, it's clear.
Okay, thank you. So I'll move ahead. So like if you see any linear algebra book, you will have a lot of portion dedicated to matrix. The reason for that is for any linear transformation, you can represent that as a matrix multiplication. So you can represent any linear transformation as a matrix. And if you want to find the map of a vector x, that is just matrix multiplication. Okay. Also, if you have any matrix, that indeed is a linear transformation. Okay. So how do you define? So we'll do both the things. If you have a linear transformation, how can you find the corresponding matrix? And if you have a matrix, how you can define a suitable linear transformation? So the second part is more easier. So if you have a matrix A, you can define a linear transformation by A of x. This is a linear transformation. You can check those properties if you want. T of 0 would be A times 0 would be 0, right? Then you will have T of x1 plus x2. This is A of x1 plus x2. You can split it, so it would be A of x1 plus A of x2. You can similarly prove for this alpha x also. This is easy to see. This is alpha times of A of x. So this is a linear transformation. Okay. So let's try to solve an example. So if you have, let's say, A is given by 2002 and you want to find T of u, right? T of u. So this is nothing but A times u, which is 2002, 1 minus 3. This would be 2 and then minus 6, right? Similarly, for any arbitrary a comma b, you have A of v defined as 2a and 2b, right? So you know now if you have any arbitrary matrix, how you can define a suitable linear transformation, right? That you can do just by matrix multiplication. Now let's look at the other way around. Let's say if you have some linear transformation, okay, and you want to find the corresponding matrix so that your T of x is given by A times x. So you want to find such a matrix A such that this particular transformation that is being defined, you can write it as matrix multiplication. Okay. Now, one small thing, the A that you obtained is based on basis that you choose. Okay. What do I mean by this is, so you have to choose a basis for your, let's say your T is a map from V to W. So you have to choose a basis for R3, that is your V, and you have to choose a basis for R2, that is your W. And for every unique choice, you will get unique A. Okay. So let's try to construct the matrix using the standard basis that we covered last time. So standard basis for R3 is 1 0 0 0 1 0 and 0 0 1, right? And for R2, it is 1 0 and 0 1. Okay. So now what you have to do is, I'll try to first solve this question and then try to sort of theoretically motivate why are we doing something like that. Okay. So what you have to do is, you have to find the image of every basis element of R3 or V. So if you have a map from V to W, you have to find the image of basis elements of your V. Okay. So let's do, so if we have T of 1 0 0, what is this? It is A1 minus A2 and 2 A3. So this would be 1 and then 0, right? Similarly, you can have T of 0 1 0 as this is 0 1 0, so this would be minus 1 and 0, and then you can have T of 0 0 1, this would be 0 comma 1. Okay. Okay. So this thing we have obtained. Now tell me one thing. So if you have a linear transformation from R3 to R2, okay, so what you want is that your Ax should be equal to T of X. So what should be the size of A that you should choose? Okay, so if you look at size of A, then this, let's say this is n cross m, and this m should match the dimension of X, because this should be m cross 1, then only this multiplication is well defined. So m we know, if we have R3 to R2, m should be 3, right? And what is the output that we have? Output is 2 cross 1. So if our output is 2 cross 1, our n should be 2, right? So A should be a matrix of size 2 cross 3. Okay. Now you have three vectors of size 2. How do you think you can arrange these vectors to obtain a matrix of size 2 cross 3? Okay. So what we actually do is, so to obtain A, you will write these outputs as columns of your matrix. So the outputs that you obtain, this is 1 0, then minus 1 0, and then 0 comma 1. Okay, this is how you will obtain your, okay, this should be 2, I think. I think I've made a mistake. So this is 2A3. So this output should have been 2 here. If you take 0 0 1, so it would be 2 here. So this is the matrix that you will obtain. Okay. Any doubt on how to construct matrix, then I'll sort of try to theoretically show you why do we do something like this. Okay. So I'll continue. See, let's say you obtain your matrix in such a way. Okay. So whatever process I define, you obtain your matrix in such a way. Now, if you want to obtain image of any arbitrary matrix, like arbitrary vector, let's say x, y, z, then you can write x, y, z in terms of basis elements of your R3. Okay, let's call this E1, E2, E3. Okay, then you can write it as x times E1 where E1 is a vector, plus y times E2 plus z times E3. Okay. So finding a, let's say this is V, this vector is V, AV is equivalent to multiplying A with x times E1 plus y times E2 plus z times E3, right? As you know, this is a linear transformation. Matrix multiplication is a linear transformation. You can split this to obtain x times A of E1 plus y times A of E2 plus z times A of E3. Okay. Now you see what happens. If you multiply AX, right? Last time I mentioned how we can interpret matrix multiplication when we multiply a matrix by a column. Let's say if my A is this, let's say this is C1, C2, C3. That's why I said many a times this interpretation would be very useful. Okay. So if you multiply this matrix by a column vector x, y, z, this is nothing but x times C1 plus y times C2 and z times plus z times C3, right? Can you draw some similarity between these two things that I have written over here? This statement over here and this over here, right? So you can see, like, if
They
we
are
choose
same.
our, yeah, you have something to say?
No, no, they are same. That's what similar.
Sort of same. So C1, if you compare, your C1 is A times of E1, right? If you compare these two things. And your second column of your matrix A becomes A times of E2. Now, what is A times of E2? It is the map of your first basis element or the map of your second basis element. That's why we wrote maps of our first basis element as first column, map of second basis element as second column, and map of third basis element as third column. This was the reason. Okay. So it is not something that we are using some tricks to write that. It is theoretically that we are doing that. Okay. Okay. We have one more example. You can tell me the matrix for this particular transformation. I'm sorry, this is to clear again. Okay, so you can try the second question. It is 6:29. I'll wait till 6:34. You can give 4 or 5 minutes to just try to write the matrix for this, and then we'll match whether we all obtain to a same answer. So you can choose again the standard basis for both of them, as I mentioned. So for R2, you can choose 1, 0, 0, 1, and for R3, you can choose 1, 0, 0, 0, 1, 0, 0, 0. So anybody obtained a matrix or some other answer, anything that you have obtained, you can probably type.
First column vector 102.
Okay, so first column is 102.
Second is 10 minus 1.
Anybody else obtained the answer so that we can cross check this answer?
Yes, sir. Correct, sir.
Okay, so I'll just briefly try to solve and then we can move ahead. So we'll use these basis elements. Let's call this E1, let's call this E2, and V1, V2, V2, V3 maybe. Okay, so what is T of E1? This is 1, 0, 2, and T of E2 is again 1, 0, minus 1. Okay, so we just need to write these as columns and you will obtain your answer. Okay, now let's do a very simple question. But I said that if you choose special, so if you choose different bases, you will obtain different matrix. Okay, so let's say we define T of x1 comma x2. Let's say we just reverse their order. Okay, so if you obtain using standard basis, you can see that you will obtain a matrix of form 0, 1, 1, 0. So if you use standard basis. Okay, now let's try to use some other basis. Okay, this is a map from R2 to R2. On the domain side, I again choose the standard basis. Okay. On the codomain or the range side, let's say we choose a basis like 1, 0 and let's say 1, 1. Okay. Let's choose this basis. Okay. So if you have some other kind of basis, let's name them also. Let's call this B1. Okay, this is E1 and E2 because these are standard basis. And let's call them B1 and B2. Now, how do you obtain matrix with respect to some other basis? Okay, so again, we will do the same thing. T of E1. This is like if you write it normally in terms of standard basis, then T of E1 is nothing but 0, comma 1. Now, whatever answer you have obtained, you have to write this answer in terms of basis element of in terms of B1 and B2, in terms of your new basis. Okay, so how we can write this? So we can write this as B2 minus B1, which is 1 times, minus 1 times B1 plus B2, right? We can write it like this. So in
The
terms,
T of E1 will be 0, 0, no?
no, this is
T
x2
of
comma
E1.
x1. So
X2
1,
comma
0.
X1.
Okay, so 1,
So,
0 becomes
yeah.
0, 1. Okay.
Okay.
So in the matrix, now you will write coefficient corresponding to these. Okay. So the first column would be minus 1 comma 1 rather than the 0 comma 1 that we had. Okay. And similarly, T of E2 is now 1, 0. This is simple. This is again B1 plus 0 B2. Okay. So this would be 1, 0 only. So this is the matrix that is corresponding to this particular choice of basis. Okay. Now if you obtain, let's say, so this is, let's say, A. Now if you obtain AX, right, let's say for A of 1, 0, right, what you will obtain if you multiply this by 1, 0, you will obtain minus 1 comma 1, right? But this is not the answer that we should have expected. So how to reach to the final answer again is that again you will do minus 1 times B1 plus 1 times B2. So if you have obtained a basis in this way, then after you obtain the output in terms of simple R2 or standard basis, you again need to change them to standard basis. Okay, I hope this was clear. Okay, so we have more example on this. I'll probably skip this one and we can move ahead. Okay, any doubt you can please ask, right? Okay. Okay. So last time we saw, what do we, yeah, last time we saw what do we mean by orthogonal vectors? Right. So two vectors v1 and v2 are orthogonal if their dot product is uh, 0. Probably I'll do this question towards the end when we have covered this inner product space. Then I can sort of more freely explain this thing. Okay. I'll cover this towards the end. Okay. Okay. So till now we talked about linear transformations. Now we want to talk about something like length and angles. Okay. We did some discussion on this last time also, but today is going to be more rigorous. Okay. I from my side have included one more thing, that is metric space. The reason is I'll probably explain why I have included this. Okay. Okay. So the question is, how do we find distance between 2 points? It's a very simple question. Let's say I want to go to this CNG filling pump and I want to start from, let's say, this Venkateshwar hospital. Okay. So this is a map from Dwarka, Delhi. So this is Venkateshwar hospital and this is CNG filling pump. How do I calculate distance between these 2 points? Okay. So the distance that we know, the Euclidean distance, what does that do is, so it will probably find its x1, x2 coordinates or y1, y2 coordinates, and then it would be x1 minus y1 square plus x2 minus y2 square. This would be its distance. So what distance would that actually depict is, if you draw a straight line from this Venkateshwar hospital to, let's say, the CNG filling pump, the distance of this line is given by this Euclidean distance. Okay. But is this distance useful for us? We can't fly like crows, right? We have to follow roads. Okay. So alternate distance was suggested. So this was sort of motivated from Manhattan distance. If some of you have played, if you have visited Manhattan, then it's great. If you have played this GTA games, they have a Manhattan map. So the map, you will see that they have these roads crossing at 90 degrees, right? So you have many roads parallel to each other and crossing at 90-degree, covering the complete Manhattan area. Okay. So similar structure I could see in Dwarka. That's why I use this map. So if you take this straight line, this purple one that I have drawn, and this purple one, so you have to find the distance from here to here, from here to here, you have to find the distance of this straight line, then add the distance of this particular straight line. Then you can obtain a distance that can give you the accurate distance that we want to use between these two places. Okay. So this is something that is known as Manhattan distance. This is given by x2 minus x1, right, plus y2 minus y1. So for this sort of thing, so right now we have sort of moved this this way. Let's say my roads were like this. Okay, this is my x-axis, this is my y-axis. I wanted to reach from here to here, then this distance is nothing but this is y2 minus y1, and this is x2 minus x1, and then I'll add both of them. This is just a sort of a twisted transformation of that. Okay. So this is given by Manhattan distance. Now the question is, this was based on, let's say, distance between 2 points in a city. Okay. When you're dealing with some machine learning models, there also you might need to find distance between 2 points, let's say. Okay. Maybe distance between two images. Okay. You might be interested in finding distance between two images or speech signals or all sort of things you might be interested in. Then what are the basic properties of our original distance that you should preserve so you can define your own distances? Okay, that's what we are going to cover in metric space, or we are not going to cover actually metric space. We are just going to define what a metric is. Okay, what properties you should preserve. Okay, so like in maths, if somebody is from mathematics background, then this is needless to say. But what happens is, let's say you study something and you want to generalize this thing, then what you do is you take some properties of original thing, you list it down, and you make these as the definition for the generalized thing. Okay. So for example, for Euclidean distance, we define Euclidean distance like this. Now we observe some properties of Euclidean distance, and we define this as a definition for a distance. Metric is just a more mathematical name for distance. Okay. So metric means distance. Okay. More mathematical name. Okay. So what are the properties that we are preserving is, first one is that distance between any 2 points should be greater than equal to 0. This is very much logical, that you want distance to be greater than equal to 0. Okay. So we saw that Euclidean distance satisfies this property. So we included this in definition, that distance between any 2 points x and y should always be greater than equal to 0. And it can be 0 if and only if my x and y are same point. If they are not same point, then I should have non-zero distance between these 2 points. Okay. This is the most basic thing that we can assume. Second point is that if I go from x to y, or if I come from y to x, my distance should be same. So distance between x and y and x should be same, right? Third property, which is the most non-trivial property, is called as triangle inequality. So like if you might know this property, right? If you draw any triangle, if you take sum of any two sides of the triangle, the sum is always greater than the third side, the length of the third side. So this, if you draw any triangle on the straight line, the length of these two sides would always be greater than the third one. Or if you take any any combination. So if you take any two sides, the length, sum of the length is always greater than the third side. That is the motivation behind this triangle inequality. So here, how were we measuring the length of a side? So we are taking the distance between these 2 points. That is the length of this side. So rather than using, even if you rather than using Euclidean distance, if you use any other sort of notion of distance, then also this property should be satisfied for a triangle that you draw in that particular space. Okay. So this is the basic idea. So this is known as triangle inequality. So if you define a function, so what are distances? Distance is a function which takes in 2 points and maps it to a real number. Okay. And it satisfies these two property, then you can call it as a metric or a valid distance. Okay. Okay, I'll include an example of calculating nullity. Okay, probably from the above examples, I'll define nullity and what is rank, and then I'll do that after discussing this. Okay. Okay. So let's take a example, non-trivial example of a distance. So we defined Euclidean distance we have talked about. Then we talked about Manhattan distance. Now this is something known as discrete metric. Okay. So how do we define this metric is, if your x is equal to y, you define distance between 2 points to be 0. Otherwise, you always define the distance to be 1. Okay. And this is a valid metric. Okay. This is a valid metric. Okay. So you asked about the nullity. Probably we can do it for these two examples that we already covered. Okay. So, okay, I'll solve this for this. I think I had other things, but I'll solve this for nullity and rank probably will calculate. Okay. Okay. So before calculating nullity, we need to understand what is null space and range space. Okay. Now, one thing you see, let's say if for some vector v, p of v is 0. Okay. Then what we can say is that if we have some t of alpha v, that is also equal to 0. Okay, so if this is your vector, if you take any vector on this particular line of any length, if any vector is going to 0, then the whole line will go to 0. Okay, so if you have any non-zero vector going to 0, then you have a complete space of vector that is going to 0. Okay, this is one thing. Another thing that I want to say is, let's say if you have v1 going to 0, t of v2 going to 0, then their sum will also go to 0. By property of linear transformation, this will split and the sum will also go to 0. Okay, so if you see these two properties, this serves as a valid definition for subspace. Okay, so what I mean by that is, so set of all vectors such that t of v is equal to 0 forms a subspace. So subspace of v. By v I mean, let's say v to w, this is a map from v to w, subspace of v. So here it will form a subspace of R3. Okay. Then dimension of this subspace is called rank. Sorry, it's called the nullity. I'm really sorry. This is not the rank. This is called the nullity of the transformation. Okay. Now we talk about range space. Okay. The range space is, let's say if you take the second example. Okay. Now, if you look at the V, okay, V's dimension is only 2. Okay. So you will have some T of V1. Okay. Let's say if V1 and V2 is your basis, then you will have some T of V1 and then you will have some T of V2. Okay. So you can only map to 2 dimensions. By that, what I mean is, let's say if you have T of V1, this is T of V2, and because my space is R3, I can find a vector independent of these two vectors. Let's call that W. Okay. So what I'm trying to say is, if you have a transformation from a smaller space to a larger space in terms of dimension, then the set of all vectors that you can map to is a strict subset of the complete set. Okay, for linear transformation. So for example, here you have second element as 0. So you will have other elements in R3 also for which the second element is non-zero. So all the set of all the range of your transformation is a strict subset of your complete space. Okay, so this is strict subset. This is not equal to. So this subset also forms a subspace. Okay, you can verify this. And the dimension of this particular subspace is called the rank of the transformation. Okay, I hope the definitions are clear. Okay, so we will try to find the null space and the range space for, let's say, the first example. We'll do one example for you. T of A1, A2, A3 is given by A1 minus A2, comma 2, A3, right? So we want to find A1, A2, A3 such that my T of V is 0. Okay, so I want to find all such vectors such that their map is 0. Okay, so what actually we want is that this vector A1 minus A2, comma 2, A3, this must be 0. Okay, so when can we obtain something like this? So if you look at the second element, we want to A3 to be 0. Only case when it is possible is that my A3 is equal to 0. Okay, now this is A1 minus A2 is equal to 0, or this would mean A1 is equal to A2, right? So what condition did we got? Okay. The condition that we got is that A1 is equal to A2 and A3 is equal to 0. Now, I'm not sure if I covered this in last class or not. If you have to find, let's take a slight detour. You have to find the dimension of a subspace. Dimension of a subspace is, so you just remember this 3-4 words that I'm going to say next, is number of independent choice. Okay. If you are given with some vector space, you are given with some subspace, you want to find the dimension of that subspace, you just need to look at number of independent choices. Okay. Now, what I mean by number of independent choices, for example, in this question, you see you have 3 things to fill. Okay. So you have A1, you have A2 with you, you have A3 with you. Okay. Now, based on these conditions, how many independent choices you can make? Okay. So your A3 is already fixed. Your A3 can only be 0. So for A3, you can't make any choice. Like you don't have a choice what A3 you should pick. Okay. Now the second thing is your A1 is equal to A2. So as soon as you pick your A2, your A1 becomes fixed. Or if you as soon as you pick your A1, your A2 becomes fixed. So based on this condition, you have only one independent choice to make. So either you can choose A1 or you can choose A2. Okay. So as I said, the dimension of a subspace is number of independent choice. So the dimension of this null space that we have defined becomes 1, and that is equal to nullity, right? I'll do one more probably example on this dimension of subspace. Okay. Before that, we can look at the range space. Okay. Now, T of A1 comma A2 is given by, sorry, A1 comma A2 comma A3 is given by A1 minus A2 comma 2A3. Okay. So best way to sort of find the dimension of your range space is you find map of your this standard basis element. Okay, so if you take T of E1, the way we found out over here, I think we pushed it down. Yeah. So this is what we obtained. Where did we shift that? Okay, I erased that. Wow. Okay. So T of E1 would be 1 comma 0, right? Then it would be minus 1 comma 0, then it would be 0 comma 2, right? This is T of E2. I hope now you can see what I'm doing. So you have to find you have to find the dimension of this particular set. Okay, so you can see this vector and this vector is already dependent. So you can multiply this by this. So you can sort of ignore this particular vector. You can see the first and third one are independent. So the dimension of this set becomes 2, or the rank becomes 2. Probably I'll solve one more question, then it would be more clear. Okay, so the nullity you obtain to be 1, rank you obtain to 2. One small theorem I can include over here is known as rank nullity theorem. Actually, I didn't had this on plan, so I didn't included it here. So I'll include. This is called rank nullity theorem. So what does this do for you is, so if you calculate one of rank or the nullity, you can obtain the other via this theorem. Okay. So let's say you have a linear transformation from V to W. What does this say is your rank of T plus your nullity of T is equal to dimension of V. So in this example, you had a map from R3 to R2. So dimension of V is 3, right? Your nullity is 1. and rank is 2. It is verified. So if you had obtained nullity, from there you could have straight away jumped to rank being 2, because finding dimension of V is not very difficult in the examples that we'll do. So rank of R3 is 3, R2 is 2, something like that. Okay. Okay, so let's do one more example, then I'll ask if it is clear or not. I'll do the same example that is included over here. So R2 to R3 is A1 plus A2. So this is the question. P of A1 comma A2 is equal to A1 plus A2 comma 0 comma 2A1 minus A2. Now let's try to find the nullity first. So what do we mean by nullity? So we want T of V is equal to 0. So we want this to be 0. That would make A1 plus A2 equal to 0. 0 is already 0. We need not do anything. And 2 of A1, this is A1, minus A2 is equal to 0. Right? This would imply that A1 is equal to minus times of A2. Right? And then this would imply that A1 is equal to A2 by 2. If we merge these two things, what would it mean is that minus A2 is equal to A2 by 2, which is possible only when my A2 is 0, right? And if my A2 becomes 0, because my A1 is minus times of A2, then my A1 also becomes 0. Okay. So what are the conditions that we obtained? So we obtained A1 to be 0 and A2 to be 0. Now how many independent choices do you have? You can't choose anything for A1, you can't choose anything for A2. So independent choices are 0. So your dimension or the nullity is 0. Okay. So you can straight away see that the rank of V, it is from R2 to R3. So dimension of V is 2. So rank should be 2. But we can verify that too, right? So if you find the images, this is 2 0. I think some of you only solved. No, it was
But
1 0 1 2.
there are three in the range space. There are three elements, no?
Range space,
So
there are three
nullity
elements.
and rank is 2. So nullity should be dimension of nullity should be 1, no?
No, no. See, so
This
the
or
rank nullity theorem says rank plus nullity is equal to dimension of V. So if you have one
dimension
transaction,
is 3, no?
no, no. The,
T
if you
of
have
A by.
transaction P to
Okay.
W, V is the
Ah,
space from where you are mapping.
okay.
This is 2. Okay. And the other element that you obtain is 1 0 minus 1. You can see that these two are linearly independent. You can't obtain one from other by scalar multiplication. Okay. Any doubt in this discussion before we move ahead?
Sir, in the previous example you told, can you please explain how you got the rank
Okay, how do we
where
obtain rank?
nullity was 1?
So nullity was 1. What do you do is you take all the mappings, right? You take the mappings of your basis element, and I obtained this set. This much is clear. I obtained this set.
Okay, sir.
So I have to see how many independent vectors I have in this map. Okay. So this first one and the third one are independent. Second one, you can see if you multiply the first one by minus 1, you will obtain the second one. So I have ruled out the second one. And that's why my rank came out to be 2.
Okay, okay, thank you.
Okay. Okay, so it's 7:02. Let's take a break for 5 minutes. And yeah, it's a too long hour session, so I don't want to keep stretching it for 2 hours continuous. So let's take a break for 5 minutes. We'll meet again at 7:07.
Sir, please retain the slide like this so that we can note that.
Okay, I'll retain this, but I also will upload this after this session. You can access it from there also if you want.
Fine, sir.
Okay. Okay, I'll start again. So, like before discussing this rank and nullity, we had a small discussion on what are metrics. Okay, so we had some properties related to metric. I just wanted to, even if you don't remember these properties, so you just remember that you can define an arbitrary distance and you have some property that you have to satisfy. So if at some point in some application you want to define a special type of metric or some special type of distance, you can just look at some book on metric space or something of that sort, and you can verify whether that property is satisfied or not. Okay. Okay. Next thing that we're going to define is norm. Okay. Norm is a more mathematical name for length. Okay. We discussed this last time also, where we saw L2 norm, L1 norm, and arbitrary LP norm for vectors. Okay. We just discussed this for vectors. Okay. You can also define these for matrices. Okay. So right now, what I'm saying is, we define it for any arbitrary vector space. Okay. So similar to distance, again, we pick some properties from, let's say, L2 norm or those kind of norms, and we write that as a definition. Okay, this is a basic way of generalizing things in mathematics. Okay, so what is a norm? Norm is a function from V to R. The distance used to take 2 entries. For length, you only want 1 entry. You want to find the length of a vector X, let's say. Okay, and it maps it to R, and it should satisfy these properties. Okay. First property is that length of a vector should be strictly greater than equal to 0. Nothing fancy over here. Okay. You want length to be greater than equal to 0, right? And you want it to be 0 if and only if your x is 0. So if you have any non-zero x, the length should be non-zero. This is my first property for now. Second property is, let's say this is my vector. Okay. Now I'm multiplied by 2. So it goes twice in the same direction. The length should be equally transformed. Okay, so let's say if I take length of 2 times of x, it should be 2 times of x. Why this mod over here? This says even if you take it in opposite direction. Okay, let's say this is the minus of x. The length remains same, right? Only the direction changes. So this mod is to take care of that directional change. Okay. Second property satisfy, and third property is again the triangle inequality that we know. Okay, so length of x plus y should be less than equal to length of x plus length of y. Okay, so these are the 3 properties of norm. If you can define a function which satisfies these 3 properties, you can define your own norms. Or there are many existing norms in literature too. 3 we discussed. One norm that I didn't discuss last time, I want to discuss, is called as infinity norm. Okay, so let's say you have a vector of form x1, x2, xn. Infinity norm of x is given as maximum of your x1, x2, xn. This is your infinity norm. Okay, this is also useful sometimes. Okay. Now, very small thing that I want to say. There is a relationship between these things that I'm defining. Okay. So if you define any norm, from that norm, you can define a distance. Okay. So let's say you have a norm. Okay. Then you can define a distance. Let's say this is d of xy is given by norm of x minus y. So you have 2 vectors here, x and y. You take their difference and you take norm of that difference. Then you can verify that this is a valid distance or metric. So from any norm, you can define a valid metric. So you can cross check that. So you have L2 norm given as the norm of x1 square plus x2 square, right? And so on. And if you talk about your this is Euclidean norm, right? L2 norm or Euclidean norm. When you talk about L2 distance, we don't call it L2 distance, we call it Euclidean distance. That is given by x1 minus y1 square, right? Plus x2 minus y2 square. You can see this, there is a similarity in the same way. Okay. So you can define in same manner distance from any norm. But the other way around is not true. So if you have a distance, there is a possibility that it is not derived from any norm. Okay, so it is not derived from any norm. If you want, if you are from maths background, you can take this as an example. So it is known that this, let's say this discrete metric can't be derived from any norm. Okay, so this relation is sort of one way. So from norm, you can reach to a distance. Okay, any doubt in definition of norm or what norms are? Okay.
Yeah, it's clear.
Okay, thank you. Okay, so we talked about angles last time. Okay, and how did we define angles was that we have a dot b given as a b cos theta. From here we can obtain cos theta. So a dot b divided by norm of a into norm of b, and we can obtain a theta from this cos theta, right? This is how talked about angles. Now this inner product is a generalization of this dot product. Okay, so dot product is a special type of inner product. So dot product again, similar to dot product, this inner product will also take two entries. Okay, so this is from B cross B. I have written it wrong over here. So this will take two entries. This is from V cross V, and it will give you an R. Okay, and it will satisfy these properties. Okay, these are sort of slightly non-trivial as compared to like norm, but they are easy to understand. Okay, so what does this mean is, if you take x plus z and you take its dot product with y, you can see that this will split. So if you have x plus y dot z, this is same as x dot z plus y dot z. So same properties applied to your inner product also, that this is inner product between x and y plus z and y. Okay. Again, if one of your element or one of your vector is multiplied by some scalar c, that scalar will come out. Okay. This third property is slightly, it is intuitive. Let's say how it is intuitive. So if you have inner product between x and y, and you have inner product between y and x, then they are complex conjugate of each other. So if you are dealing with real number, this will be same. You need not worry about it. But many a times you have complex numbers involved. That's why this property come into picture. So if you have inner product between x and y and x, they are complex conjugate of each other. You should remember this. Okay. And the fourth property says is, if your this inner product should always be greater than 0 as far as your x is not equal to 0. If your x is 0, then you can have inner product to be 0. Otherwise, it should be always greater than 0. Okay. So these are four properties by which you can define any inner product. Okay. Now you have a similar property from any inner product. You can define a norm. Okay. So how do you define? So a norm of x can be given by inner product of x with itself. Okay, so you can verify that if you take dot product of x and x. Okay, so norm square is given by this. Okay, x and x. So you can take either, you can define x as under root of this, right? So x comma x is x1 square plus x2 square plus x3 square. So this dot product leads to your Euclidean norm, and then your Euclidean norm leads to your Euclidean distance. Okay, these are all sort of related things. So again, you can have a hierarchy where from inner product space, you can reach to a norm, and from a norm you can reach a metric, but other way around is not always true. So this is not true, this is also not always true. Okay. Okay, I hope this is clear.
Yes, Norm, it is clear.
I'll continue. So next thing that we're going to cover is eigenvalue and eigenvector. Okay. So the more focus is going to be on solving questions. I'll just define what are eigenvalues and eigenvector, and then we'll move on. Okay. Okay. So now the question is, okay, let's say you have a linear transformation T. Okay. The question is, does there exist a vector x for which T of x don't change its direction, but it just scales it? Okay. So it is lambda x. This is the question. Okay. So what is the set of vector for which T of x is equal to lambda x? If such x exists, that x is called eigenvector of that linear transformation. So this is a very simple definition, that if you have an x such that T of x is equal to lambda times x, then that x is called eigenvector, and this lambda is called the corresponding eigenvalue. Okay, so this is eigenvalue for this particular x. Okay, so you can have, and this eigenvector is for this particular eigenvalue. Okay, so yeah, one more thing over here is that you want your x to be non-zero. Okay, because if your x is 0, then this is very trivial. T of 0 is always equal to any lambda times 0. Okay. So lambda t x is equal to 0 is not at all an interesting case. So we want to restrict as our x to be non-zero. So we want to search for only non-zero x such that T of x is equal to lambda x. Okay. Now, how do we solve them? Okay. So if you take this lambda x to this side, right? So this would make T of x minus lambda x is equal to 0. Then you can take T minus lambda I of x is equal to 0. Okay. Now what does this mean? Okay, so I think we didn't cover this thing earlier, but I'll just give a brief sort of intuition. So let's say you are solving Ax is equal to 0. A system of equation you are solving Ax is equal to 0, right? When do you have a unique solution and when do you have a non-unique solution? Okay, so let's say if your A is invertible, you can take A inverse on both the side, and you can have x is equal to A inverse of 0 is equal to 0. So this means if your A is invertible, the only solution to Ax is equal to 0 is when your x is 0, if your A is invertible. And I'll just say this, if your A is not invertible, right? If your A is not invertible, then you have some non-zero solution. Okay. Okay. One more very, very small observation. Because you are looking at T of x is equal to lambda x, these transformation are from same space to same space. Then only you will obtain x on the right hand side also, right? So all these A matrix that you would obtain would be square in nature. So you need not worry that it is a rectangular matrix. That's why its inverse is not defined. All this would be square matrix. If their inverse does not exist, then you will have some non-zero solution. Okay. Now, what we wanted is that T of lambda I times of x is equal to 0. And we also want our x to be non-zero. So what eventually we want is that our T minus lambda I is not invertible. This is what we want. And if you sort of recall your class 12th days or something like that, a matrix A is not invertible. Okay, so A is not invertible is same as saying that determinant of A is 0. If your determinant is of A is 0, then your matrix is not invertible, and vice versa. Okay, for a square matrix. So what we want is, that determinant of T minus lambda I is equal to 0. So a way of finding out your eigenvalue is solving this particular equation for lambda such that determinant of matrix T minus lambda is equal to 0. Okay, so let's try to solve some question. If you repeat this thing, things would be more clear. Okay, so this is A. This question, in this question, you have to check whether V1 and V2 are eigenvectors for A. Okay, so A of V1 is 1, 3, 4, 2, 1 minus 1. This is 1 minus 3, this is minus 2. This is 4 minus 2, this is 2. This is minus 2 times of 1 comma 1 minus 1. So V1 is an eigenvector. This is an eigenvector with an eigenvalue minus 2. Okay, this is just based on the definition of eigenvalue. Again, A of V2 is 1, 3, 4, 2, 3, 4. This is 3 plus 12 is 15. 12 plus 8 is 20. This is 5 times 3, 4, which is equal to. So again, this is an eigenvector with the eigenvalue lambda is equal to 5. Okay. Okay. Just give me a minute. I'll be back in a minute. Okay, sorry for the small delay. I had some other creativity. Okay, sorry. So now we'll solve an example where we have to find eigenvalue of a given matrix. Okay. So let's say we are given with a matrix A. What I said is, if you want to find eigenvalues, first of all, so you should solve for determinant of T. Over here, T is just your A minus lambda I is equal to 0. This is what we should solve for. Okay. And this I is your identity matrix if it is confusing some of you. Okay. So let's solve this. So this is determinant of 1, 4, 1, 1 minus lambda times 1, sorry, what am I writing? 1, 0, 0, 1, right? And I want this to be 0. This implies determinant of 1 minus lambda 1, 4, 1 minus lambda is equal to 0. This again implies 1 minus lambda square minus 4 is equal to 0. You can solve this now, right? Lambda square plus 1 minus 2 lambda minus 4 is equal to 0. This would mean space. This is lambda square minus 2 lambda minus 3 is equal to 0. Square minus 3 lambda plus lambda minus 3 is equal to 0, or lambda minus 3 plus 1 lambda minus 3 is equal to 0. This means lambda is equal to 3 and lambda is equal to minus 1. Okay. So we have obtained our two eigenvalues, which are lambda is equal to 3. So our eigenvalues are and lambda is equal to minus 1. Okay. So let's sort of try to find out corresponding eigenvectors too. Okay. Eigenvector. Okay. So what was the simple definition for eigenvalues? That A of x should be equal to lambda x. From here we reach A minus lambda I x should be equal to 0. Now we know the value of lambda, so we can find x, right? So matrix was 1 1 4 1. So let's try to solve for lambda is equal to 3. So 1 1 4 no, it was 1 1 4 that way. 1 1 4 1 minus 3 times I is 3 0 0 3. This times x is equal to 0, which is equivalent to saying minus 2 4 1 minus 2, right? x1 x2 is equal to 0. Okay. What does this mean? This means that minus 2x1 plus 4x2 is 0, or x1 is equal to 2x2. This we derive from I don't know from why I wrote like this. Okay, let's use the standard way. Okay. So if you multiply this thing, you will get minus 2x1 plus x2 is equal to 0, or x2 is equal to 2x1, right? And from second row, you will get 4x1 minus 2x2 is equal to 0, or x2 again is equal to 2 times of x1. Okay. So from both the things, we are getting the same option. So we have this condition. X2 is equal to 2x1. Okay. Now one small thing. Let's say Ax is equal to lambda x. You take c times x. Then what is A of c times x? This is c times of Ax. This is c. This is lambda x, or this is equal to lambda times of cx. Okay. What do I mean by this small calculation is, for any eigenvalue, you will not get only one eigenvector, but you will get a whole space of eigenvectors. So if x is your eigenvector, then c times x is also an eigenvector. Okay. So this forms a subspace. Okay. Again, with the dimension, you can calculate based on the number of independent choices. For example, here you had x2 is equal to 2x1. So you can only pick one of these two, right? Other one gets fixed. So dimension is 1. Okay. So when you are asked to write an eigenvector, you can write any one element of this subspace, and the others would be generated by this only, right? So eigenvector you can write, you can pick any arbitrary. So for example, if I take x1 to be 1, then x2 becomes 2. So this is an eigenvector because this satisfies this property. I can write any vector satisfying this property. Okay, so this is an eigenvector for lambda is equal to 3. Okay, similarly, let's now I did calculation in elaborate way. Let's try to do it over here for lambda is equal to -1. So for lambda is equal to -1, a minus lambda x is equal to 0 would mean that this is 2, 4, 1, 2, x1, x2 is equal to 0. This would mean 2x1 plus x2 is equal to 0, or x2 is equal to minus 2x1. You can see that from second row also you will obtain the same condition. So an eigenvector can be written as 1 comma minus 2. Okay. Okay. So one more very small thing, I'm not sure whether it is required for machine learning applications or not. So there is a property that we called as diagonalization. I'm not sure whether it was covered or not. Diagonalization. So if you have a matrix A, for some special type of matrix, you can write those matrix as some V, D, V inverse. Okay. So for matrix, let's say if you have a matrix of 2 cross 2 of rank, let's say 2, okay, and if you are able to obtain two linearly independent eigenvectors, okay, or for example, if it is an n cross n matrix with rank n, and you can obtain n linearly independent eigenvectors, you can write this in this form. So for example, in this case, this was a 2 cross 2 matrix where both rows were independent, 1, 1 and 4, 1, you can't get another by scaling other. And you have two linearly independent vectors. One is this 1 comma minus 2, and one is that we obtain corresponding to 3, that is 1 comma 2. Okay. Then you can write it in this form. How you can obtain this form is, so this D matrix you obtain by writing eigenvalues on diagonal entries. Okay, rest everything is 0. And V you can obtain by writing your eigenvectors as columns. So first you wrote 3 over here, so you should write eigenvector corresponding to 2, and then corresponding to the second one, and you can write the suitable inverse over here. Okay, why is this important? So it has sort of more than one application, but the application that I want to discuss with you is, let's say you want to find a to the power 100. Okay, so one way is that you can keep doing multiplication, 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 or let's say we'll start with a square. Okay, so this is v dv inverse because my a is now v dv inverse, again v dv inverse. Now this v inverse into v becomes identity, so this can be written as v inverse. Similarly, you can sort of expand a to the power 100, you can write as v d to the power 100 v inverse. Now for a diagonal matrix, let's say your matrix is 2, 0, 0, 1. If you multiply with another diagonal matrix, what you will obtain is, this is 2 square, this is 1 square, 0, 0. And for a diagonal matrix, if you raise it to the power 100, you will just have diagonal entries raised to the power 100. So this would be V, this would be 3 to the power 100, 0, 0, and I think it was -1 to the power 100. Okay. So taking powers of matrix becomes very easy when you are able to diagonalize it. There are many other properties that would be covered in a full-fledged linear algebra course. Okay. Any doubt in eigenvalues and eigenvectors? If you have any, you can clear it right now, because next class we will have singular value decomposition. There we will be finding eigenvalues and eigenvector lot many more times. So if eigenvalues and eigenvectors are not clear, then you might have trouble understanding singular value decomposition too. Okay. So one question that I skipped at that moment was this orthogonal component. I said I'll cover inner product space first and then I'll come back to this. So orthogonal vectors are the one for which dot product is 0. Now because we have defined inner product, we will say that two vectors are orthogonal when their inner product is 0. Okay. So rather than dot product, we have obtained inner product. Okay. Now, let's say you have vector v1 and v2 is equal to 0. Now, rather than v2, if you choose alpha v2, okay, then v1 times alpha v2 is nothing but, as we saw, this is alpha times v1 dot v2. For real number, it would be alpha times v1 dot v2. For complex, we will have complex conjugate over here. Okay. So this is again given to be 0. Okay. So if you have a vector v1 and you find a vector v2 which is orthogonal to this v1, then you can obtain a space of vectors which is orthogonal to v1 by just multiplying it by coefficient alpha. Okay. Also, if you have, let's say, two vectors v1 and v2 and v3 which are orthogonal to v1, then v2 plus v3 is also orthogonal to v1. Okay, you can see that v1 dot v2 plus v3 is nothing but v1 dot v2 plus v1 dot v3, which is again 0. Okay. So if you take set of all vectors orthogonal to v1, you will again obtain a subspace. This is what I mean. Okay. And that is what is given by orthogonal complement. So orthogonal complement of the span of v1 would be set of all vectors which are orthogonal to this particular set. Okay. So span of v1 would be a set. So let's call it W. So let me properly define this orthogonal complement. Yeah. So let's say you are given with a set V, then V transpose is V perp you can call is defined as set of all W such that V dot W is equal to 0 for all V belonging to W. I mean, you pick any element of this set W, then W dot V is 0. If such a thing happen, you keep it in W perp or W complement. Okay. So you are given a set that is span of this and this. Okay. And you want to find the orthogonal complement of W. Okay. So how do you obtain? So you have to look for a vector which is orthogonal to this plus this. Then if it is orthogonal to both these vectors, then it would be orthogonal to any vector in this particular span, right? And if you take span of this set also, any vector here would be orthogonal to any vector here. Okay. So you have to look for such a vector. Okay. So let's look at the options. Okay. So first option is 0, -1, -1. Okay. Is it orthogonal to the first vector? So you take 0 times 1 is 0. Yeah. Somebody has to say
No.
something.
No.
Okay. So it is 0 times 1 -1 plus 1. So this is orthogonal to
Yeah,
first
it is.
vector.
Yes.
It is orthogonal also to the second vector. So first option is correct. Others option you can sort of check and you can say that it is not orthogonal.
No. Say it is not orthogonal to the second vector, no?
Which one?
The
Yeah,
very
it is
first
not
one. Yeah.
orthogonal to the second vector.
Answer is fourth, the last one, I think.
Yeah, this would obtain -2, which is not 0, right? So for the second one, I think its dot product with first one obtains 2, which is not 0. That's why it is not orthogonal. Third one will obtain 1, 1 with both. Again, it is not there. Last one obtains 0. And with the last one also it obtains 0. So fourth option is the correct option. So this is how you can find orthogonal complements. Okay. Okay, so I'll move ahead. We have some time left. we can cover something about symmetric matrices. Sorry, convex set first we'll do. I think it was covered briefly in the lecture, so we'll do. Okay. So geometrically, a convex set is such that if you draw, so if you take any 2 points in the set and you draw a line connecting those 2 points, the line should lie within that set. If such a property is satisfied, that set is called as a convex set. Okay. So for if you take a point here and here, and you draw a line connecting this point, these points, you see that your line is going out. So the set that I drew is not a convex set. So a convex set is such that, for example, this. If you take any 2 points in the set and you draw a line connecting those 2 points, the line should remain within that set. Okay. This is very much useful in optimization. If you have convex set and convex function, your life becomes very, very easy. Okay, so you can see that you take any 2 points within this ellipse kind of structure and you will obtain it. The line would be within that set. This is the definition of convex set. Mathematically, you can write a set S is convex if lambda times x plus lambda 1 minus lambda times y belongs to S for all x comma y belonging to S and lambda belonging to 0 comma 1. Okay. So what does this mean is, so this represents the line connecting x and y. Okay. If you take lambda to be 0, it represents the point y. If you take lambda to be 1, it represents the point x. And the intermediate points on the line, you keep changing lambda, you will keep getting intermediate points on the line. Okay. So this is the definition of convex set. Any doubt in the definition? Okay, thank you. So I'll move ahead. There is something called symmetric matrices. Okay. So what are symmetric matrices? You might know what is transpose of a matrix. So let's say if you have a matrix 1, 2, 3, 4, then if you take its transpose, it can be represented by T, or you can just put a dash symbol. You can use both these notation to represent transpose. Okay. So transpose, when do you do a transpose of a matrix? What you do is you convert your rows to columns. So your first row become your first column and your second row would become second column. This is what you do when you take transpose of a matrix. So it would be 1, 2, 3, 4. Okay. So for what is a symmetric matrix? So A is symmetric if A is equal to A transpose. Okay. If both your A and A transpose are same, then it is a symmetric matrix. For example, a matrix like 1, 2, and this is 3 and 3. So this is a symmetric matrix. Even if you take the transpose, you're going to obtain the same matrix. Okay. And there is something also known as skew symmetric matrix. Because I'm doing symmetric, I'll write skew symmetric too. So if your A transpose is equal to minus of A, then those kind of matrices are called skew symmetric matrix. An example can be 1, 2, 3, minus 3. Okay. Okay, sorry. This is not a correct example. The example would be 0, 0, 3, minus 3. Because in the transpose, your diagonal elements remain fixed. We want minus. So the diagonal entries must be 0. So this is an example of skew symmetric matrix. Okay, this is a symmetric matrix. Okay. Now, if you have symmetric matrix, there is a good property that you have with symmetric matrices. I think there is a question based on this. That's why I included. So for a symmetric matrix, all its eigenvalues are real. So all eigenvalues that you will obtain for your symmetric matrix will always be real numbers. Okay. One thing that I forgot to mention is when you find your eigenvalues, you solve this, right? Determinant of t minus lambda I is equal to 0. The equation that you get out of it is known as characteristic polynomial. Okay. So, for example, in this question, this polynomial that we obtained, these are all equivalent polynomials. So this is known as characteristic polynomial. Okay. So if you have a symmetric matrix and you look at its characteristic polynomial, okay, so because all its eigenvalues are real, you can't have a term something like lambda square plus 4 in it. Okay, so lambda square plus 4 times something. Okay, because then that would mean that lambda square is minus 2, sorry, minus 4, and lambda is plus minus 2. So you can't have these kind of eigenvalues. So if you look at characteristic polynomial of a symmetric matrix, then you should always have something like this. So you have a question, I think. I can't tell you the exact answer because I'm not allowed to. But this is the property that you should check, that whether the values of lambda that you are getting are all reals or you are getting some complex values. So you can use this to solve. Okay. 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 So there is something known as positive semi-definite matrix that I want to call that. And I'll define it for symmetric matrices. Okay. So a matrix, okay, a symmetric matrix A is positive semi-definite if for all x we have x transpose Ax greater than or equal to 0. Okay. So no matter what x you choose, if you take x transpose Ax, you obtain something greater than or equal to 0, then that matrix is called positive semi-definite. Okay. Okay. There is a more stricter definition. So for example, if your x transpose Ax is strictly greater than 0, then these are called positive definite matrix. So we don't have any semi down. It is positive definite matrix. Similarly, you can have definition for negative semi-definite and negative definite matrix. Okay. There is, I'm mentioning these things that might be useful. Now, there is an alternate definition or an alternate property of your positive semi-definite matrix. So if you find eigenvalues of A and all these eigenvalues are greater than or equal to 0, then also it is positive semi-definite. Okay. Similarly, greater than 0, you can define positive definite and so on. Okay. So we have an example over here. Okay. So we are going to take the eigenvalue root to check if this is an positive semi-definite matrix, negative semi-definite matrix, negative definite matrix, what it is. What is an indefinite matrix? If it is not any of the four, it is not positive semi-definite, it is not positive definite, not negative semi-definite, not negative definite, then it is called an indefinite matrix. Okay. So let's try to find this. So we want to find the eigenvalues for this. So again, I could have taken another route, but I'm taking so that I can do one more example of finding eigenvalue. This would mean 6 minus lambda 4, 4 minus 5 minus lambda is equal to 0. This would mean 6 minus lambda. Okay, let's take this minus sign outside. This is 5 plus lambda minus 16 is equal to 0. So this is minus lambda square with plus, it becomes lambda square, minus 5 lambda plus 6 lambda. This is plus lambda becomes minus lambda, plus 30 becomes minus 30, minus 60. So lambda square plus minus 56. Do we have roots for this? I think I hope I haven't made any mistake. Can we find root for this? Let's say we want to find root for this. I'll just use something to find the solution for this. Just give me a second. I'm not going to use I don't want to calculate this, rather use some software or something like that. So let's say solve. Okay, so I have used Mathematica to solve. This gives me numerical values as minus 6.30 something something, and another value that we get is 7.3 something. So you see, one of them is negative, one of them is positive. So we can't make comment about this. So this is an indefinite matrix. Okay. So if my both of them were positive, then would have been positive definite. Yeah, that's what it will do. Okay. So this is what I had planned for today. If you have any doubt in what we have covered, you can ask now. We have some 4-5 minutes left. If you don't have any doubt, then probably we can end this session.